Hi, my name is Kiana James, and this is my learning log for Math 2050. Here is my title page, my table of contents, which has everything that is in the learning log. Again, another page of table of contents. This page here is our numeration systems. The definition of a number is an idea or an abstraction that represents a quantity. A numeral is the symbol that we write, see, or touch when representing numbers. You can see here that we have the different types of numbers, the cardinal numbers, the ordinal numbers, identification numbers, and we can order whole numbers by using a timeline or a number line. We have our different numeration systems. The first one here that we see is the tally numeration system, which is where we use tally marks to identify numbers. Usually we group them by fives and we add that way. Our Egyptian numeration system is somewhat different. It has multiple symbols. The biggest disadvantage of the Egyptian numeration system, I find, is that it's too many symbols to make up a number. Like, as you can see here, 1 is a vertical staff. So if we were writing 3, we would need 3 of these. Or if we were writing 15, then we would need 1 heel bone and 5 of the vertical staffs. You can see here we also have the Roman numerals. We have these here. These are the most common Roman numerals that we use today, besides the traditional 1 through 10 numerals. We have the Mayan numeration system where they use different little symbols, and they were the first ones to actually introduce a symbol for 0. The Hindu Arabic numeration system is the numeration system that we use. So it includes 10 digits, so 0 to 9. We also have on this page exploring bases and place value, where you can see that base 10, we actually start with 0 and go through 9. Base 7, 0 to 6. And whenever you're doing bases, it's always going to be 1 less than the actual number itself. So base 3 is 0, 1, and 2. We also have here how to change bases. We can change bases by dividing, where you can factor these out. So if you want to convert 231 to base 7, you would actually divide 231 by 7, and you would get 33, and your remainder is 5. So then you would divide your 33 again, and you would get 4 with a remainder of 4. And we're going to read the number going up. So 231 converted to base 7 is 457. 450 base 7. My apologies. You can also do this by division, which is pretty much kind of the same thing as up here. The only difference is that you're actually going to use the powers of the base number that you want to convert to. Using an abacus, you see here is not much of how to use an abacus here, but the number of beads on that abacus on each row determines the base of the abacus. So if you have 4 beads on each row of the abacus, then your abacus is in a base 4. We are also learning how to work with base 10 blocks, where in fact 1 unit cube is 1, and we have what we call a long, which is 10 units, and that represents the number 10, and so on and so forth. 10 longs equal 1 flat, which is you have 10 longs going here, and that equals to 1 flat, so that's 100 units here, and so on and so forth. You have a long flat and a flat flat. The addition properties of whole numbers. We use models of addition such as the set model, the number line, and they pretty much show us how to add and subtract as well. As you know, you can subtract on the number line, you can add on the number line, and you can also count on. Another thing that we learn is making 10, where you actually, instead of having 8 here, you will put 2 more, and you will make this 10 and the remainder here. It makes it kind of easier to add that way, especially for kids. Our properties of addition, we have our closure property that says the set of whole numbers are represented as, and for any pair of numbers in a given set that is added, the result is also in that set. We'll also have our commutative property of addition, which for any whole number a and b, a plus b equals b plus a. We also have the associative property. If a, b, and c are whole numbers, then a plus b plus c equals a plus b plus c, which pretty much means that the numbers aren't changing here. It's just going to be the position of the parentheses that is changing in the grouping. So a plus b is the first group, and then we added c at the end. Then of course we can go ahead and do a plus b plus c. So whatever the sum of b plus c is, we can go ahead and add a. So that's pretty much what it's saying. And those two things should actually be equal out to each other. The identity property of addition means that we have an identity number. So our identity number in addition is, of course, 0. So we know that any number, which is a, plus 0 equals that same number, and vice versa. 0 plus any number equals that number. Our subtraction concepts. We learned the takeaway concept, which is a pretty traditional and standard concept when it comes to subtracting numbers. Because you know that I can have a total of 8, and I can take away 3 and get my answer, which I would have 5 left. The comparison concept is also another thing that we can do, because what you can do is line up the amount of things that somebody has, and wherever that amount stops, that remainder is actually your answer. And of course we have the missing addend and the number line, as I have stated before. You can add and subtract in different bases. As you can see, 12.5 plus 31.5. It added out nicely to 435. This one, however, we had to borrow and we had to change a few things. So we know that 3 plus 3 equals 6. So a 6 is 1 5 and 1 1, meaning that it's one group of 5 plus an extra 1. So we would actually take that and write that here. And 1 plus 1 equals 2. So we know that it's 2 5s and 0 1s. So then what you want to do is go ahead and add up your 5s and your 1s, and you will get 315. Same thing goes for this one here, as well as the subtraction. As you can see, the subtraction one ended up nicely, but this one over here had to do a little bit of extra work, right? So 325 minus 145. Well, we can't subtract 2 from 4. So we had to actually borrow a 5 from here. So when we borrow a 5 from here, instead of having 3 5s, we have 2 5s. And we're going to add those 5s to that 2, so that gives us that 7. And then we're going to subtract as usual. 2 minus 1 is 1 5. 7 minus 4 is 3 1s. We can also do this with time. With time, yards, feet, and inches, as well as the subtraction here, as you can see. Multiplication and division of whole numbers. We do know that the two numbers being multiplied together is the factors, and the outcome is our product. There's multiple ways that we can multiply. The repeated addition model, meaning that we can take the same number and add it so many times over. So here I added 3 plus 3 plus 3 plus 3, which equaled out to 12. We can do a number line model where we can actually skip those spaces in between those numbers. So we skip 3 spaces and hit 6, then we skip another 3 and hit 9. We also can do a bar model where we can add equal size bars and repeat a number of times. Our array is actually one of the most common used ones as far as what they are learning today in Common Core curriculum. You can construct an array where each point would be, you would count those points and that would be your answer. Then of course there's the area model where you can do 2 on the side and times 3 at the top. We also have the Cartesian product model, where if we have a schedule and we have 2 histories and 3 languages that we can choose from, and we're trying to find the possible outcomes of each combination, we are ultimately left with world history. We could take Latin, German, French, ancient history, Latin, German, French. And if we do that, we can have Latin and ancient history, German and ancient history, French and ancient history, French and world history, German and world history, and Latin and world history. So the total amount of incomes that is on the side here would be 6. So 2 times 3 equals 6. We also have properties of multiplication, such as our closure property, which the product of any 2 whole numbers is also a number. So A times B equals a whole number. We also have the cumulative property for multiplication. If A and B are whole numbers, then A times B equals B times A. The associative property, A times B times C equals A times B times C. Meaning, if we have 4, 2, and 3, 4 times 2 times 3 equals the same thing as 4 times 2 times 3. So if I have this here, first I'm going to multiply 2 times 3, which will give me 6. And then I'm going to take that 6 and multiply it by 4, which will give me 24. Same thing here. I will take the 8 from 4 times 2 and multiply it by 3. And that will give me the same answer of 24. We have our identity property for multiplication, where A times 1 equals A and 1 times A equals A. Our zero property pretty much says any number times 0 is 0. And of course, we have our distributive property, We have our models of division, our partitionings, where we split things into divided equal parts. Measurement and repeated subtraction, where we subtract the given number at a time to see how many groups are subtracted. And we also have the missing factor, where we rewrite the problem as a multiplication problem. We can also do a tape diagram that draws a picture and divides it using the missing factor to determine the amount. As far as order of operations go, it's just pin this here, parentheses, exponent, multiply, divide, add, and subtract. Our addition and subtraction algorithms. We can use a set model to go ahead and add these two things together. So 23 plus 25 is 48. Our expanded algorithm, we have 8 ones and 4 tens. So whenever we do this like this, it will still give us the same answer, but that's the same thing as saying 20 plus 5 plus 20 plus 3. And then we add those sums together. Of course, we can do left to right algorithm as well as the lattice algorithm, which the lattice algorithm is actually really, really easy. All we do is 357 plus 74. 7 plus 4 is 11. So we take 1 and 1 and put here because you can only put one digit in each one of the triangles. So this will make your 11. 5 plus 7 is 12. So we have a 1 and a 2 here. And 3 plus 0 is 3. So we have a 0 to represent that we have an empty space, and also our 3 right here. And we would get our answer. So our answer was 1, then 3, because you're going to multiply add going across. So 1, 3, and then 4. So you end up with 431. We can also do the scratch method as well as subtracting across zeros, which is actually pretty easy because all you're doing is borrowing here. This is another example of that expanded form. Breaking and bridging is where we take the first number and we add it by the tens of the second number. And then we take the answer from that and add the 1 from the second number to get our final answer. We can do multiplication using the rectangle method, which is this method here, where we'll put 10 and 3 and 10 and 2 because 13 times 12. And we'll multiply going that way. We can also use the lattice for multiplication as well as Russian peasant multiplication, where it includes halving and doubling. When we are halving, we take 24 to half of 24 is 12, half of 12 is 6, half of 6 is 3, and there is no half of 3, so we put 1. And once we get to 1, we stop. We then cross out any rows that have even numbers on the halving side, and we add the rest. Here, this is that example of that repeated subtraction that we can do in division. You see we have 6 groups of 15 as well as 10 15s here. We can also do long division, where we divide, multiply, compare, and bring down, as well as short division, which is more of a mental math.